Today we're going to begin looking at Unit 5, which is on different types of reactions. Next week when we meet, we're going to be doing reactions pretty much all week long for mission week. So it's important for you to understand what those reactions are before we get to them. So that's what we're going to spend today doing. So there are four main types of chemical reactions. We have synthesis, combustion, decomposition, replacement, and there are single and double replacements. So those are the four main ones. A synthesis reaction, okay, there's a couple types here. This is when you have one of a couple of things happening. So when you have two elements that react, and you could form one product. So that's like you have element A plus element B, yielding product AB. This reaction is always a synthesis reaction when you have two elements reacting. So an example of this is if you had, say, sodium metal reacting with chlorine gas, giving you sodium chloride. You have two elements combining to form one compound. And don't forget Cl2, just because it is Cl2, it is diatomic, but it is in its elemental form, right? You never see just pure chlorine, so don't forget that. You can have an instance where you have two compounds that can combine to form one compound. So you have two different compounds combining to form one. And that's what this instance is right here. You have calcium oxide, CaO. If you put that into water, you get calcium hydroxide. So you get, starting with two compounds, you form just one. Another option is you can have a compound and an element combined to form one compound. So down here we have sulfur dioxide reacting with oxygen gas to give us sulfur trioxide. Okay, some things about this, just things to recognize synthesis reactions. You always start with two or more reactants and you always end with one product. Okay, that's synthesizing something, you're bringing it together. So that could be two elements, it could be two compounds, it could be an element and a compound. Some general side notes about synthesis reactions. A couple of things. First of all, these tend to be very energetic and exothermic, which you might remember is a term from last semester, meaning it lets off a lot of heat. These reactions usually get pretty hot. And in addition to that, they also tend to have very toxic and dangerous, we'll just say, reactants and products. So just kind of peeking down here, synthesis reaction-wise, sodium metal is not something you want to come in contact with. Chlorine gas is not something you want to come in contact with. Sodium chloride's okay. So this isn't everything, but a lot of things that go into the reaction are very dangerous. Calcium oxide, not something you want to ingest or be around a whole lot of. Water is okay. Calcium hydroxide, strong base, stay away from that. And then down here you got sulfur dioxide. You do not want to breathe that in. That's pretty much toxic fumes. And sulfur trioxide is even more toxic. So just some things to keep in mind. You won't see a lot of synthesis reactions because they are pretty dangerous. They also let off a lot of heat, so it's pretty dangerous to do these things inside of a building. You have seen one of these, though, earlier this year when the reaction outside that we did of aluminum plus iodine yielding aluminum iodide, ALI3. You probably remember seeing that as the purple smoke reaction that let off a lot of iodine gas as that product was forming. So that was a synthesis reaction where we took powdered aluminum, added in, we ground up some iodine, put it together, we put a couple of drops of water on it, took it outside, and then it reacted. So that is one that you have seen and probably one of the safer types of synthesis reactions. Okay, a combustion reaction. So it's going to require oxygen, combusts with a substance, and releases energy in the form of heat and light. So this is going to let off heat and light. You might always think of this as when you're trying to combust something or burn it, it's going to let off a good bit of energy and usually some kind of light. So some combustion reactions are also considered synthesis reactions. So this one, for instance, is carbon plus oxygen yielding carbon dioxide. So this one just has two reactants and one product. Notice right here Okay, oxygen has to be one of the reactants. It must be one of the reactants for it to be a combustion reaction. And this one just was basically charcoal, right? If you have a Weber grill at home or a charcoal grill, that's pretty much what you're doing. When you heat that up in the presence of oxygen, you are letting off CO2 gas. Okay, you see the charcoal glowing, letting off, right, the light and the heat's coming off, and you also let off carbon dioxide. This example is a synthesis because you have two elements forming one compound. Another example here is if you take something like methane. Okay, this is what's coming out of your gas faucets in the labs. Okay, it's natural gas. They dope it with some sulfur compound, so it smells bad, but most of it is methane, CH4. And if you're going to burn that, you have to have it in oxygen. So you have to have enough oxygen in the room to do this. When you do that, you get carbon dioxide as a product and water. And you might start noticing some common themes here, is that the products always include CO2 and usually include water. Okay, and for our purposes, combustion reactions are probably always going to have carbon, some kind of carbon compound as a reactant. You can have combustion reactions with metal. You can have, for instance, or you might recognize this, iron plus oxygen, right? That's if you like leave iron outside or like an old barbed wire fence. That's going to form iron oxide. Well, iron 3 oxide to be specific. This is something reacting with oxygen, and even though this is a slow process, it does, as each individual iron atoms, as the individual iron atoms convert over in the presence of oxygen, it does let off a slight amount of heat. You're probably not going to see any light because it's such a slow process, but this is in fact a form of combustion. It's just very slow and not really very obvious to you. Okay, decomposition reactions. This is a reaction in which a single compound breaks down into two or more elements or new compounds. So this one is usually very easy to recognize. This means you are starting out with one compound. In this instance, compound AB breaks apart into one or more things. Okay, substance A plus substance B. This breaks into two or more things, I should say. One reactant breaking down into more than one product. So just a couple of real-world examples here. Down below, we have something called sodium azide. I'll write that down, sodium azide. Okay. And so some of these decomposition reactions happen quite quickly. Sometimes you just need to give it the right kind of spark to get it going. This one, for instance, down below here, just requires a small amount, it's almost shock sensitive, and once it goes, it breaks apart, you get sodium metal, so here's sodium just breaks apart in the sodium metal, and you get nitrogen gas. And so where is this used in the real world? Well, a reaction that just a little bit of a spark that produces a little sodium metal and a lot of gas, this is used commercially in airbags. Okay, so that's what you have inside of most vehicles. Well, they may or may not all use this, but a lot of them do have it. And so as soon as it gets a little electrical impulse, that NaN3 breaks apart and you get a lot of gas, specifically nitrogen gas, which is a good thing to choose if you're trying to fill an airbag. Okay, if you fill that airbag with, say, something like O2 gas, that's problematic because now you're in a vehicle that has been in a wreck with a very combustible gas. So that's something you really want to have there. You don't want to fill it with hydrogen gas because that is also combustible. So you did a good job, whoever was picking here, picking nitrogen. It's a pretty inert gas for all of our purposes. Another example of something that happens is if you were to break down, for instance, this compound here, hydrogen peroxide, which is H2O2. And you probably have this at home, probably up in your medicine cabinet. It's probably in a brown bottle. And why is that? Well, it's because over time it is sensitive to light and it will break down. And you're going to get a couple of products here. You're going to get water, and you're going to get oxygen gas. So they actually use hydrogen peroxide as a source of pure oxygen gas if you know what you're doing with it. But this is a slow reaction. Even if you put that in a clear bottle, a decent chance it lasts at least a few days, maybe a week, depending on the amount of light, maybe even a month or two. It will last actually a decent amount of time. It doesn't happen immediately. Whereas down here, all it takes is one little tiny electrical impulse and the whole thing goes off. So just a couple of examples of real-world decomposition reactions. Okay, now we're moving into the replacement reactions. So this is the last type here. These are going to be when things change places, is kind of the way to think about replacement reactions. So this first one, a single replacement. This is a reaction in which the atoms of one element replace the atoms of another element in a compound. So this is like if you have element A plus compound BX becomes compound AX plus element B. So they've kind of switched places there. A and B have switched places. A real-world example of this, and we'll see this on demonstration week, as we have first of all here solid lithium. That's what's powering your batteries, right? Lithium-ion batteries. If you put a piece of solid lithium into water, okay, so you have an element here, lithium plus compound water, so BX here is water. The lithium changes places with one hydrogen, so not both of them, just one of them. And so what happens is, in comes the lithium, it's replaced a hydrogen, now you're left with lithium, and look at this, that is a hydroxide ion. So you're left with lithium hydroxide. This is your new compound that's formed, and then hydrogen comes off of that, but remember, hydrogen has to come off in the form of H2, right? Elemental hydrogen is not just H, it is H2. So here's a real-world example of that, where you've got an element replacing that element in a compound. There are some other ones here. You've got an example of metals replacing hydrogen or another metal. So that's the first kind, and that's the one that you just saw here. You have a metal, lithium, replacing hydrogen or some other kind of metal. So it's going to switch places with the hydrogen. The hydrogen is going to become the element in that first one. The second one here, you've got a piece of solid copper, and you're going to put it into a solution of silver nitrate. Okay, so you're going to take the piece of solid copper, stick it in the beaker full of silver nitrate, and what happens over time is that you get silver plating out on this copper piece, so you get solid silver forming, and then you've got the copper that was on the solid copper goes into solution as copper nitrate. So the copper and silver switch places. Okay, they have changed places. The copper is now in the compound and the silver is now the element. This does not automatically happen, okay, so we're wondering, why does it go this way? Well, why doesn't it go backwards? Why doesn't silver go and replace this copper and knock the copper out? Well, it's got to do with relative reactivities, which we'll see here in a moment. So if you try to reverse this process, okay, it's not going to happen naturally. You're actually going to have to apply some electricity to it to run it backwards. But silver is not going to replace the copper. It's not going to knock out the copper. So we'll see why here in just a moment. So here's a table of relative reactivities, starting with the more reactive things at the top, okay, and the least active things down at the bottom. And we're going to box off here the halogen chart, because we'll come back to that here in just a moment. So let's find our two that we were just talking about. We were talking about copper and silver. All right, and on the list of active metals, copper is more active than silver. So that means that if copper is in its elemental form, it will replace silver if silver is in a compound. Okay, that's what that means right there. But it won't go the other way around. The silver will not replace the copper. So that means anything up above here, you put any of those in a solution that's got silver ions in it, and they're going to switch places. So, single replacement types, another type is you have a nonmetal replacing another nonmetal. There we go. Okay, this is usually involving the halogens, so family 7A, fluorine, chlorine, bromine, and iodine. And there's also a reactivity for these. So, in this instance, remember this is nonmetal can only replace nonmetals. So this is fluorine gas. Okay, fluorine can only replace the a nonmetal. Well, the nonmetal in the other substance here is bromine, not sodium. Can't replace the sodium. It's a nonmetal replacing another nonmetal. And this will happen if you go back and look at the activity series just on the previous slide. That will happen. The fluorine is at a higher activity state than the bromine, so that will occur, and you'll end up with sodium fluoride. And actually what ends up happening if you're bubbling fluorine gas through a solution of sodium bromide, you'll actually get liquid bromine forming in it. Okay, that will occur. Now, if you try to go the other way around and you got sodium fluoride in solution and you try to, say, bubble some bromine gas through there, it's not going to happen. The bromine is not more active than the fluorine, so you get no reaction in this situation. So just taking this as an example here, if we've got something like, say, solid zinc plus, and let's just say for our purposes, how about, copper nitrate, copper 2 nitrate. And we look over here on the side, and you're asked, well, what's going to happen here? Am I going to have a reaction? Well, first thing you should do is identify where those two metals are on the activity series. Zinc is at a higher activity state than the copper is, so therefore the zinc will replace the copper. Okay, it will go in, that'll knock the copper out, so that means your products over here, you're going to get solid copper coming out of that, and now the zinc is going to go into solution, so you end up with plus, and then zinc's going to have a +2 charge, so ZnNO3 2. Okay, so that's what we end up getting out of that. Okay, double replacement reactions. So the last one of these general reaction types. This is when you have the exchange of ions between two compounds. A way to identify it is by looking for two compounds reacting, and you still end up with two compounds as a product. So if you have substance AX plus BY, you end up with AY plus BX, so the A and B have switched places there. Alright, an example of that, it's deleted my arrows from my formatting, so I apologize, I had to write them in. You have calcium hydroxide plus hydrochloric acid, and you'll learn the names of the acids because we haven't learned those yet, is going to yield calcium chloride plus liquid water. Well, what's happened here? If we consider calcium is A and that hydrogen is B, okay, these two things are going to switch places. Okay, and we end up with, now the calcium is bonded with the chlorine, so we get Ca, and then it's got to be Cl2 because the calcium still has a +2 charge and the chlorine still -1, so it's got to be this. And over here, now that this hydrogen has come over here to bond with the hydroxide ion, well, now you have an H plus an OH, that is H2O, so you get liquid water. Looking at this one right here, you've got sodium plus copper 2 chloride. Okay, I'll draw my arrow in there. And so you're going to have the sodium switch places with the copper, and the copper is going to come back over and bond with the hydroxide ion. So you end up with sodium chloride, NaCl, since the sodium's +1 and the chlorine's -1, plus copper 2 hydroxide. The copper's got +2, hydroxides are each -1, so you got to have this formula. All you're doing here is switching one thing, right? A is switching with B, B is switching with A, so they go back and take each other's places. Some nice things about this, another way to recognize double replacement reactions is that they will always form one of three things. They're going to form water, a precipitate, or a gas. Okay, so if you see that forming and you've got two reactants and two products, then decent chance you have a double replacement reaction. This first one, all right, that's the one for the previous slide. Okay, calcium hydroxide plus HCl, it forms water. Okay, we were switching the Ca and the H, formed water, so that was our giveaway there. Here on this one, it's mismarked on your notes, so I have to fix it here. I don't know why I put it in as aqueous, but in this instance, you might remember this from the previous lab. You have sodium hydroxide, aqueous, plus aqueous copper 2 chloride. Okay, that's going to react and form aqueous sodium chloride, and you get a solid out of this. Okay, you might remember that we talked about the term precipitate in the last lab. I said it's a solid that forms from the reaction of two solutions. So you're going to get a precipitate. In this instance, it's copper 2 hydroxide, CuOH2. Okay. The last option is a gas, and for our purposes, if you mix two compounds together and you're getting a gas, it's probably not safe to breathe in, and you should probably let me know that that's what's happening. They generally tend to not be very safe. So for instance, this is potassium cyanide dissolved in water, okay, and this is now you're mixing it with hydrobromic acid, so also dangerous thing. This will kill you, this will kill you. Yielding potassium bromide, which in small quantities probably wouldn't kill you. Plus, this is hydrogen cyanide, which is now the gaseous form of cyanide, and that will also kill you. They use this to fumigate old buildings back in like the 1910s, 1920s to kill all the vermin walking around. So very dangerous stuff there. But this is the gas, HCN. So another way to check to see, okay, things to give away that you've got a double replacement reaction. So you've got two reactants, two products, and the products you have to include one of those three things. Okay, this is just a nice summary chart with all of that. There should be some problems for you on the Section 1 worksheets that you have to identify what kind of a reaction it is. So this is a great nifty chart to help you keep track of what's actually happening. So I would probably have this open while you are going through that. And that's it.